Hello and welcome to Electromagnetics 1. Dr. Trample here. This is lecture number 23. We'll be talking about the Smith chart today. Well, what exactly is the Smith chart? The Smith chart is a graphical representation of the impedance of a transmission line and the corresponding reflection coefficient as one moves along the line. We will assume here that the Smith chart is applied to a lossless transmission line, which is to say that the characteristic impedance of the transmission line is purely real. The Smith chart is constructed within a circle of unit radius as shown in Figure 1. So let's have a look here at Figure 1. We have two axes, first of all, that I want to explain. The horizontal axis is the real part of the reflection coefficient, and the vertical axis is the imaginary part of the reflection coefficient. Okay? This blue circle here has a radius of 1, which corresponds to a magnitude of the reflection coefficient equal to 1. Now, the construction of the chart is based on the relationship between the reflection coefficient, the load impedance, and the characteristic impedance of the line. As seen here in equation number 1, you can see that the reflection coefficient is equal to the impedance of the load minus the characteristic impedance of the line divided by the sum of the impedance of the load and the characteristic impedance of the line. We can also write the reflection coefficient in magnitude and angle form as in here, so it can be written in terms of a magnitude and an angle, or a real and an imaginary part in this way. Going back to Figure 1, you can see here that this is the magnitude and angle expression of the reflection coefficient, which also corresponds to a particular point in xy coordinates, which correspond to the real part and the imaginary part of the reflection coefficient. Well, in order to avoid working with a separate Smith chart for each characteristic impedance, for instance, you may have several different transmission lines with different characteristic impedances, for instance 60 ohms or 100 ohms or 120 ohms. So to avoid that, we introduce the normalized impedance, which is to say you take the impedance of the load and you simply divide it by the characteristic impedance of the transmission line. That's called the normalized load impedance, and it's denoted by little z sub l. And that normalized load impedance has a real part denoted by little r and a imaginary part denoted by little x. Okay? You can then write the transmission or the reflection coefficient, as the normalized impedance minus 1 divided by the normalized impedance plus 1. We can solve this equation here for the normalized impedance in terms of the real and imaginary parts of the reflection coefficient. When we do that, it turns out that the normalized load impedance is equal to 1 plus the reflection coefficient divided by 1 minus the reflection coefficient, or if we expand the reflection coefficient in terms of real and imaginary parts, we get this expression, equation 5. Now, once we separate the reflection coefficient into real and imaginary parts, it has to be true that the real part of the right-hand side here is equal to little r. Similarly, the imaginary part of the right-hand side is equal to little x, the normalized reactance. And so by multiplying top and bottom of this fraction by the complex conjugate of the denominator, we can separate the right-hand side into a real part and an imaginary part. When we do that, turns out that the real part of the normalized impedance is given by this expression in terms of the real and imaginary parts of the reflection coefficient. Similarly, the normalized reactance is given by this expression in terms of the real and imaginary parts of the reflection coefficient. We can rearrange equations 6 and 7 in the following way to arrive at equations 8 and 9. So just using some algebra, we can rearrange equation 6 to look like this. We can rearrange equation 7 to look like equation 9. Now, if you look very carefully, equations 8 and 9 are both equations for circles. How does that work? Well, imagine you have an xy coordinate system now. The equation for a circle is x minus x naught squared plus y minus y naught squared equals the radius squared. In equation 8 here, the role of x is played by the real part of the reflection coefficient, and then x naught, which is the coordinate of the center along the x-axis, the coordinate of the center of the circle along the x-axis, is right here, little r over 1 plus r. The coordinate of the center of the circle along the y-axis is 0 because nothing is subtracted off from the imaginary part before we square it. And similarly, the radius of the circle is simply 1 over 1 plus little r. Equation 8 is therefore an equation for a resistance circle or an R circle with a center, as I mentioned here, at r over 1 plus r 0 and a radius of 1 over 1 plus r. Let's take a look at some typical R circles here. Okay, let's look at the R circle corresponding to little r equals 0. That corresponds to a shorted load. The little r equals 0 circle is on top of the magnitude of gamma equals 1 circle that we mentioned before. That makes qualitative sense because if your load is shorted, all of the energy is going to reflect back. None of it's going to be absorbed. And it's going to, so therefore the magnitude of the reflection coefficient is going to be equal to 1. If you look at the equation here for the center and radius, so for the R circles, again, they're centered at some point along the x-axis, okay? And the radius is 1 over 1 plus r. So as r increases, the center of the circle is going to move to the right here along the real axis. And you see that here. The center of the r equals 0.5 circle is somewhere in here maybe. The center of the r equals 1 circle is somewhere in here, etc., etc. So the center of the circle moves to the right, and as you increase the load resistance, the radius of the circle shrinks down all the way down to this point right here that corresponds to little r equals infinity. That is an open circuit. So this circle right here, the unit circle, corresponds to a short-circuited load. That point corresponds to an open circuit load. All right, now similarly, equation 9, this equation right here, describes what's called a reactance circle, and it has a center at x equals 1, I should say along the x-axis here at 1, and then along the y-axis at 1 over the normalized reactance there, and has a radius of 1 over the normalized reactance. Figure 3 here shows some typical reactance circles for x equals 0, plus or minus 0.5, etc., etc. Okay. So again, if we look at where the center should be, we know the center is always, the x-coordinate of the center is always here at gamma r equals 1 along the horizontal axis, which I've sort of been calling the x-axis. And then the vertical coordinate, the gamma I coordinate, is at 1 over x, which is the normalized reactance. So as the normalized reactance increases, the center of the circle will decrease. It'll get closer here to the x-axis if you want to look at it from that perspective. So for instance, here we are at, this is the x equals 0.5 circle, and its center is going to be way up here somewhere, say, I guess it needs to be over this line, way up here someplace maybe, and its radius is bigger than the x equals 1 circle, who has a center maybe down here somewhere, and a smaller radius. Okay. Of course, you can have both inductive and capacitive loads, and so we need to have inductive and capacitive lines here on our Smith chart. In fact, we do. Now, if we plot the r and x circles on the same set of axes, we arrive at the Smith chart. Let's have a look at the Smith chart in all of its glory here. Okay, here we go. This is in fact the Smith chart. You can see that we've got all of these different r circles on here. The outer one, that's r equals 0. And here is r equals 0.5, r equals 1, etc., etc. And then all of these other circles are reactance circles, and they're labeled here. So this is x equals 1, this is x equals 0.5, etc., etc. Okay. Well, there are a number of important things to notice here about the Smith chart. Okay, the first one is that the point P sub SC corresponds to r equals 0, x equals 0. That is a load impedance of 0 plus J0, okay, which is the short circuit load point on the transmission line. At point P sub OC, we have r equals infinity, x equals infinity, which corresponds to a load of infinity plus J infinity. So POC right here is the open circuit point on the line. Okay, so if you simply leave the transmission line open, you're at that point on the Smith chart. If you short the transmission line, you're way over here, 180 degrees away. Those are two important points. When you move, point 2, when you move 360 degrees around the Smith chart, that represents a distance of lambda over 2 along the transmission line. So this is all sort of normalized to the wavelength, okay, of the wavelength that you're using. So as you move all the way around the Smith chart, 360 degrees, that corresponds to moving half a wavelength along the transmission line. Clockwise movement, when we move along this direction, we're moving toward the generator. And counterclockwise movement, moving along this direction, means we are moving toward the load. All right? Okay. There are 3 scales around the periphery of the Smith chart here, and I'll show you the figure 5 just momentarily. The scales are used in determining the distance from the load or generator in degrees or wavelengths. Okay? The outermost scale is used to determine the distance on the line from the generator in terms of wavelengths. The middle scale determines the distance from the load end in terms of wavelengths. So outermost scale tells you the distance from the generator. The middle scale tells you the distance from the load, and it's all in wavelengths. Okay. The innermost scale is a protractor that's used to measure the angle of the reflection coefficient. All right, let's have a look here at figure 5. Okay. So here we go. Here's this outermost scale here. And this outermost scale is telling you how far away you are from the generator in wavelengths. Okay? This middle scale tells you how far you are away from the load, and the innermost scale here tells you the angle of the reflection coefficient. All right? Back up to the notes. Now, since a lambda over 2 distance on the line corresponds to a movement of 360 degrees, lambda distance on the line corresponds to a 720 degree movement on the chart. So if you want to figure out where you will be a distance of lambda along the line, you have to move around the chart twice, essentially. Okay. Another thing to note is that the Smith chart can be used as both an impedance and an admittance chart. Remember, admittance is simply the reciprocal of the impedance. As an admittance chart, the normalized admittance, which is the admittance of the load divided by the admittance of the line, is written little g plus jb. So this is the normalized conductance, and b is the normalized susceptance. The little g and little b circles correspond to the little r and little x circles, respectively. We'll do an example at the end of the lecture where I will show you how exactly this works. Okay. Let's go back here just for a moment to Figure 5. The second half of Figure 5 shows you the corresponding movements along the transmission line. So, again, when we move in a clockwise direction along the Smith chart, we are moving toward the generator along that direction. When we move in a counterclockwise direction, we are moving toward the load. Okay, now let's talk about matching. The single biggest and most useful use, as far as I'm concerned, of the Smith chart is matching. We're going to talk about quarter wave matching, and we're also going to talk about stub matching in this lecture. Okay. Well, what does it mean for a load to be matched? When the characteristic impedance of the transmission line is not equal to the characteristic impedance of the load, we say that the load is mismatched, and a reflected wave exists on the line. You can see this very simply from the definition of the reflection coefficient. Let's see if I can find that here real quick. Right here, equation 1. Clearly, if ZL is equal to Z naught, then gamma L is going to be equal to 0, and then you won't have a reflection. However, for maximum power transfer, which is often desirable, it's desired that the load be matched to the transmission line. In other words, we would like the load impedance to be equal to the characteristic impedance of the line, so that we don't have a reflection. The magnitude of the reflection coefficient is equal to 0. The matching is achieved by using shorted sections of transmission lines. Okay. Now, recall that for a lossless line, the input impedance is given by this equation right here. If the length of the line is a quarter wavelength, or lambda over 4, then beta L is equal to, beta is 2 pi over lambda, the length is quarter wavelength, lambdas cancel, 2 over 4 is 1/2, and we get pi over 2. Okay, and so the input impedance becomes Z naught times ZL plus J Z naught tangent pi over 2 over Z naught plus J ZL tangent pi over 2, like that. If you notice, so a tangent of pi over 2 is, the magnitude of that is infinite. So the numerator begins to basically looks like j z naught times a very, very large number. The denominator, it looks like jzl times a very, very large number. The tangent of pi over 2's in a sense cancel out, and the term in parentheses starts to look like looks like z naught over zl. So the total impedance, the input impedance, excuse me, then is equal to z naught squared divided by zl. Or if we divide both sides of the equation by z naught, zn over z naught, which is the normalized input impedance, looks like 1 over the normalized load impedance. Okay, or in other words, the input impedance here looks like the normalized input admittance, essentially. So when you add a quarter wavelength line on the Smith chart, you obtain the input admittance corresponding to a given load impedance. So that's one of the things that you can see if you attach a quarter wavelength line to a load. If you measure the input impedance, you'll be measuring the admittance of the load, the normalized admittance of the load. That's what you'll be getting when you measure that. So that might be a useful measurement to be able to make. However, a mismatched load can also be properly matched on a line that has characteristic impedance Z naught by inserting a transmission line that's quarter wavelength long with a characteristic impedance Z naught prime prior to the load, as shown in figure 6. So let's have a look down here at figure 6. Okay, so if you place a quarter wavelength length transmission line right in front of your load that has a very specific characteristic impedance Z naught prime. This Z naught prime is not going to be equal to the characteristic impedance of the line that you're trying to match. In fact, Z naught prime is given by the square root of the characteristic impedance of the original line and the characteristic times the characteristic impedance of the load. Okay. That lambda over 4 length of transmission line is called a quarter wave transformer. And again, going back to our original equation here and now substituting in square root of Z naught and ZL where we used to have Z naught, suddenly you can see that the input impedance, looking into that quarter wavelength transformer, is equal to Z naught times ZL, the square root, squared. So that's just Z naught times ZL divided by ZL. ZL's cancel, and you just get the characteristic impedance of the line. Okay. We're assuming here that Z naught prime, Z naught, and ZL are all real numbers. So that's one very simple way of matching a load to a line is simply inserting a quarter wavelength transmission line that has a very specific characteristic impedance. Now, oftentimes you don't necessarily have a length of transmission line with the correct characteristic impedance. So we can also match sources. We can also match lines to loads using what's called stubs or stub tuners. Stub tuners are short lengths of transmission line used to cancel out unwanted reactance in microwave circuits. The single stub matching network consists of 2 transmission line sections, one of length L connecting the load to point A, and another of length D connected in parallel with the other 2 lines at A. What is he talking about? Well, let's look here at figure 7 to see an example of a stub matching network. Okay, here's an example of a stub matching network. We've got a load, and there is a length L. So the stub matching network consists of two lengths of transmission line. One of length L connected from the load to point A like this, and then another of length D connected at point A like this. And you'll see that this particular stub has been shorted. It's got a wire at its termination. You can also have open circuited stubs. We'll be focusing primarily on the shorted stub because the open circuit stubs tend to radiate energy, which is not always preferential. Okay, again, the matching network consists of two lengths of transmission line, one of length L, one of length D. Okay, the length L1 is connects the load to point A, and then the one of length D is connected in parallel with the other two lines at A. The second line is called the stub. The length D1 is called the stub, and it is usually terminated in either a short or an open circuit, as I mentioned, and hence its input impedance and admittance are purely reactive. Let's and again, the one that is in figure 7 there has a short-circuited termination. Okay, let's have a look at the reactances of some of these. Let's see if I have that. Guess I don't have that in this particular set of slides. Okay, let's look at an example to see how in practice you would actually use the Smith chart to match a load to a particular transmission line. So this is example 11.7, an antenna with an impedance of 40 plus J 30 ohms is to be matched, so that's the load, the antenna is the load, is to be matched to a 100 ohm lossless transmission line using a shorted stub matching network. All right, we need to find A, the required stub admittance, B, the distance between the stub and the antenna, that's length L, C, the stub length D, and D, the standing wave ratio on each segment of the system. Okay, well, first of all, how do we figure out what the stub admittance needs to be in order to have a match? Okay. Well, the first thing we do here, the first step to use the Smith chart to do this, is to calculate the normalized admittance of the load and plot it on the Smith chart. Okay, so in this case, what we'll do first is calculate the normalized. First, what you do is probably calculate the normalized impedance. In this case, that's going to be 40 plus J 30 divided by 100. Then take the reciprocal, and that turns out to be, for the normalized load admittance, that turns out to be 1.6 minus J 1.2. Let's look and see where that falls on the Smith chart here. Okay, so we're at R equals 1.6. We're on the R equals 1.6 circle. I understand this isn't terribly big, but if you look along the horizontal axis here, that number right there is 1.6. And so this circle right here is the R equals 1.6 circle. So that is, you know that your load is on that circle somewhere. Then you look at the reactive part, which is negative in this case, and that, let's see, what was that number here? It was minus what? Minus 1.2. Okay. If you look along the lower, if you look along, oops, wrong chart. If you look along the lower half of our circle here, you can see each of these admittance curves are also labeled. Here's 1.8, and here is 1.6, and here is 1.4, and here is 1.2. That's the one that we want. So where this minus 1.2 admittance circle intersects with the R equals 1.6 resistance circle, bam, that's the point where we start on the Smith chart right there. Okay. All right, now what do we do? Okay. Next, draw a circle with a radius that's equal to the magnitude of your load admittance. Okay. Well, the distance from the center of the Smith chart to the point of our load admittance right here is that length. So you just take a protractor and draw a circle just like that. That blue circle corresponds to a circle that has where the magnitude of the load admittance is constant all the way along that blue circle there. Okay, now what do we do? All right, we've drawn our circle. Such a circle centered at the origin is a circle of constant magnitude of the reflection coefficient gamma also. Okay, so along that blue circle, not only is the magnitude of your load the same, the magnitude of the reflection coefficient is also constant along that circle. All right. Now, the next thing we want to do in order to achieve the match is find the points A and B where that constant magnitude of gamma circle intersects the G equals 1 circle. Okay, back down here again. All right. Okay, well, where is the G equals 1 circle? It's the same as the R equals 1 circle right here, the one that passes through the center of the Smith chart right there. So that blue circle intersects this R G equals 1 circle at that point. We call that point B, and at that point, which we call point A. Refer to my notes here. Okay, now we have to read off the admittance at each of those points A and point B. Okay, it looks like at A we have, let's see, let's look at the admittance here at point A. Okay, how do we do that? Well, you find the admittance circle that passes through A, this one right here. That corresponds to an admittance of positive J 1.04. So right there, that you read that number, see here's 1.0, here's 1.2, so that point is about 1.04. Now let's go down and look at point B. All right, the admittance circle passing through point B is right here. That is between, again, 1.0 and 1.1. And that is also, that one turns out to be minus J 1.04. Okay? All right. Okay, so the required stub admittance then is going to be equal to basically the normalized stub admittance right here is right here. So to unnormalize it, we simply multiply by y naught. Let me go back up here and show you the equations. Okay. All right. So the stub admittance has to be equal to plus or minus J 1.04 over 100. Why? Why? Why does it work that way? Okay. Let's go back to our Smith chart. Okay. If we are down here, let's say we're going to choose point B to do our match. Okay. In order to achieve a match, we have to move from point B somehow to the center of the Smith chart. The center of the Smith chart corresponds to G equals 1 or R equals 1 plus J 0. That corresponds to an input impedance equal to, when you unnormalize it, equal to the characteristic impedance of the transmission line, which is by definition of a match. So right here at the center of the Smith chart, that's the match point. All right. So what we need to do is we need to add an admittance that will cancel out the admittance at point B. All right. So if we're at point B here, we're going to actually have to add a normalized admittance of J 1.04. When you do that, what will happen is you will move along the G equals 1 circle right there down to the origin. All right. It makes a certain amount of sense, right? If you add admittance, the real part is not going to change, but you're going to move along this circle right down here to the origin. If you choose point A to do your match, point A again corresponds to positive J 1.04, then you must add negative J 1.04. You must add a reactance of minus J 1.04 in order to move from point A along this G equals 1 curve down to the origin in order to achieve the match. Okay, let's go back and look at the equations here. All right. Okay. So again, at point A, you need you're going to have to add minus 1.04 normalized, or when you unnormalize it, it turns out to be minus J 10.4 millisiemens. If you're at point B down at the bottom, you're going to have to add negative, or you're going to have to add positive J 10.4 millisiemens. All right, it just depends. Okay, again at point A, that's where the admittance was positive. You have to add negative admittance to cancel it out. At point B, where you had a negative admittance, you have to add a positive admittance in order to cancel it out, to get yourself to the center of the Smith chart. Okay, so that is the answer to the first question. What is the admittance of the stub need to be? We finally have that. Okay, now the second question, part B here, that we want to know is what's the distance between the stub and the antenna? What is L? Okay. In order to determine L, we have to use, again, the Smith chart. Let's go back and look at point A. If we're using point A to do our match, right here, okay. If we're at point A, what we're going to do is we're going to be looking at these outer three these outer three charts, or I should say these outer three scales on the Smith chart. Okay, so in order to achieve the match, we had to move from where we started here at YL up to point A. Okay. The question is, how many wavelengths long is that in terms of the length of the first part of the stub, the L length stub? Okay. In order to figure that out, what you do is you come and you put a line through your starting point out all the way through the outer circle like that. Okay. And you're going to read the position in degrees where you start from. Let me show you that in the equations. Okay, right. point A, we started at, looks like about minus 39 degrees, okay? And we ended at, let's read off where point A is. Okay, from point A, we ended at what looks like about, yeah, maybe 60 some, I think it is, degrees. Yes, call it 62 degrees. Okay, that's where this number comes from. Right here, okay. So the total electrical distance we've moved here is 62 minus 39 divided by 720 degrees. We divide by 720 degrees because that corresponds to one wavelength. We're trying to figure these distances out in wavelengths, okay? Okay, and then at point B, let's look at point B. Oh, first of all, we have to explain where this lambda over 2 comes from. Okay. All right. Why are we subtracting out the 360 degrees, in other words? Or why do we subtract it from 360 degrees? Okay. Even though what we did is we measured this angle right here, okay? We measured this angle, which was minus 39, or I should say 62 minus the negative 39. But where we're actually moving, remember, we're actually moving from the load toward the generator. That's actually clockwise. So the distance you actually move is from here all the way around to there, okay? That angle is lambda over 2, which that angle is 360 degrees minus that angle. So this angle here is 360 minus this angle that we found. Okay, so remember 360 degrees corresponds to lambda over 2 on the Smith chart. So the actual angle that we moved is this one right here. So we actually moved, again, moving from load to generator from here to there at point A. Okay, now point B is just a little bit simpler, fortunately. All right, from point B, in order to get from point B, we start at, come back down here. Remember, we started at negative 39, and we just moved down here to negative 62 degrees. Again, it's a little hard to read off this chart, but if you look at where this thing crosses, it's right around minus 62. Okay, so the distance, again, because we're always moving in practice, we're always moving from the load toward the generator here when we move this on this chart, which corresponds to a clockwise distance. All we have to move to do the match in this case is that angular distance, which is just 62 minus 39 degrees. Again, when you divide it by 720, that comes out to be 0.032 wavelengths. The distance from A in wavelengths turned out to be 0.36 wavelengths. So if you want to use a shorter stub, then you would want to make your match at point 3 or at point B, because you only need 0.032 wavelengths. You only need a stub whose L length is 0.032 wavelengths. Again, if you don't care for some reason you need a longer line, you can also make the match at A. Okay. All right, now next question. C, the stub length D. Okay, in other words, how long, the question is, how long do we need to have the parallel length, the stub there, how long does that need to be in order to achieve a normalized admittance of negative 1J1.04 if we're doing the match at A, or positive J1.04 if we're doing the match at B. How do we achieve that? Okay. Well, we need to look at the stub length, which is the distance from the short circuit point to A prime and B prime. Okay, so let's look. A prime, that was the point that corresponded to minus J1.04. Let's look at that again. Okay, here we go. Yeah, this is minus J 1.04. So you look at, in order to see, okay, again, how electrically long does the stub section need to be? It's just the angular difference between the short circuit and A prime right there. And it's a little hard to read. It looks like it's just shy of minus 90 degrees there. Similarly, okay, how long does your stub need to be if we're going to make the match up here at A? You look at B prime, that angle, again, just shy of 90 degrees, it looks like to me. Okay. Again, we want to look at everything in terms of wavelengths. So we divide the 88 degrees there for A prime, divide by 722. That turns out to be 0.12 wavelengths. And then the match at, or sorry, excuse me. So for the match, in order to make the match at A, excuse me, we use the B prime point. All right. So again, we're always moving counterclockwise, or excuse me, we're always moving clockwise here. So to make the match at point B, we use the A prime number. That corresponds to that distance. That just simply 88 degrees divided by 720 degrees times lambda. However, again, if we want to make the match up here at A, we use this point, B prime, and that corresponds to moving, again, clockwise all the way from here, short circuit point, all the way around the Smith chart up to here, which is 360 degrees, again, minus 88 degrees. Which is why we have .360 minus 88 will get you this 272 degrees right here. And again, you divide that by 720 degrees, which corresponds to one wavelength, and that gets you the number of wavelengths. So again, to make the match at point A, in this case, you need a shorter stub length than to make the match at point B. Okay, last question. We need to obtain the standing wave ratio S. Okay. In order to do that, locate the point where the constant magnitude of gamma circle intersects the gamma R circle. Really easy. You can just read it right off. So to find the standing wave ratio S, here is our constant magnitude of gamma circle, the blue circle. And you just look right here and see where it intersects the horizontal axis. That's the point 2 there. That's the point 3. So let's call it 2.7. And in fact, that is the correct number. Standing wave ratio is equal to 2.7. So the value of R at the point where that constant magnitude of gamma circle intersects the gamma R axis, that is the standing wave ratio S. Well, thank you very much for your attention. I appreciate it. Dr. Trample signing off.